Assalamualaikum. We are from Group 6. So today we are going to present our group project, which is the topic is hydraulic impeller system. So I will share to you guys about the introduction about our piling system. So basically, a piling system is a fundamental aspect of construction engineering used to provide deep foundation for various types of structure, including buildings, bridge, and other heavy load. The primary purpose of piling is to transfer the load from the structure to a stronger subsurface layer, ensuring stability and durability. There are three types of piles, which is end-bearing piles, friction piles, and steel piles. So for the next detail, we will see in the next slide, which is we can see the design and component of the piling system, the operation and how the piling system works, and last but not least, how fluid mechanics apply in the piling system.
2.1 Design of hydraulic piling system. Hydraulic piling system design involve a meticulous process that optimize performance, reliability and safety for the intended application. Engineers consider many different factors such as the type of pile to be driven, soil condition, environmental factor and project requirement. The design usually begins with an analysis of the soil load bearing capacity and the structure requirement of the pipe. Additionally, the design incorporates safety features such as overload protection and emergency shutdown system to minimize risks during operation. Iterative testing and refinement can be performed to validate design and optimize performance before deployment in real construction project. Overall, a well-implemented design process is essential to ensure the efficiency and longevity of hydraulic pile system in various construction applications. 2.2 Component of the hydraulic piling system. The hydraulic drive system consists of several essential components that work together to effectively drive pile into the ground within the intricate framework of a hydraulic piling system. A symphony of vital components orchestrate the seamless execution of foundational tasks. Each part play a vital role in the process, ensure stability, force distribution, and precise control throughout the operation. Together, they form a cohesive system capable of carrying out various construction projects that require a strong and reliable foundation. So there are several main components in hydraulic piling system, which are as follows. Number one is hydraulic hammer. Hydraulic hammer are the main equipment of hydraulic piling system, delivering powerful blow to drive pile into the ground for construction projects such as foundation, bridge, and retaining walls. Number two is hydraulic power pack. In a hydraulic piling system, the hydraulic power pack play a critical role in driving the entire operation. This powerhouse unit comprise as hydraulic pump, reservoir, motor and control valve designed to generate the high hydraulic pressure need for pile driving. Number 3, hydraulic cylinder. In a hydraulic pile driving system, the hydraulic cylinder acts as the main actuator responsible for providing the enormous force required to drive the pile into the ground. The cylinder converts the hydraulic pressure generated by the hydraulic unit into linear motion, creating thrust of the pilot driving assembly. Number 4, ladder or mast. The ladder or mast in a hydraulic piling system serve as a crucial vertical or inclined structure component that guide the pile hammer and pile into the ground with stability and precision. This component provides support and alignment during the driving process, ensuring that the pile is accurately positioned and driven to the desired depth. Number 5 is control and monitoring system. The control and monitoring system of a hydraulic pile system serve as the nerve center, monitoring and regulating various aspects of operation to ensure efficiency, safety and accuracy. The system includes a series of control mechanisms, sensor and monitoring devices that monitor critical parameters such as hydraulic pressure, apply force, pi depth and system performance. The last one, or number 6, clamp or chuck. The clamp or chuck of the hydraulic drive system is the essential part responsible for holding the pi tightly during the pi driving process. It uses hydraulically activated jaw or clamp to provide a strong holding force, ensuring the pi remains stable and aligned when driven into the ground. That's all from me. Thank you.
Hi, Assalamualaikum. I'm Nurul Syazwani binti Abdul Hamid, and we talk about the operation and how the system gonna works. So for the preparation, the conference marks the actual pi position as per project specification and engineer plan, and it will assure alignment of the layout with structural requirements for stability and bearing capacity. So properly, the marks the site where place will be located, and then position the hydraulic peeling rigger equipment with hydraulic system and machinery, and it's ready to drive pies to required dips on the system. And lastly, ensure re-agreement and site preparation are in order, enabling the construction teams to mobilize the peeling operation for a robust and enduring foundation. And the next, for site, place the pearl in the pie guard or leader and listen in against movement with precision. So after that, alight the hydraulic hot hammer on top of the pie, ensuring proper delivery or of blows. Then check alignment to ensure the pie remains vertical and does not hinder the driving process. Energize the hydraulic system, powering the hammer's piston to lift and strike the pile hit with impact blow. Continue the process until the pie reaches the recommended dip or desired resistance, ensuring stable and lasting construction support. And the third, driving the pie. Fire the hydraulic power unit, directing hydraulic fluids into the hammer. Energize the piston with hydraulic fluid, causing it to rise and fall, pounding the pill head with force. Move the pill into the ground through the movement of the action. Modulate the hydraulic system to optimize force and frequency of impacts. Monitor variables such as pressure and pipe penetration. Make adjustment for efficient results and minimal stress or damage to the pipe and solid discussion. Scoot through the parts, monitoring and control. For this part, oversee the part driving process by monitoring critical parameters like hydraulic pressure and flow. Utilize the control system to track the progress of the part being driven. Make real-time adjustment to ensure the part is driven correctly and effectively. Adjust the hydraulic power unit to control the force sustained by the hydraulic hammer. Ensure the pie is driven to the specific dips or resistance without causing damage to the pile or surrounding screw tool. Lastly, maintain the integrity of the foundation and ensure overall safety and efficiency. For the last part, completion. Withdraw the hydraulic hammer once the desired dip is achieved, completing the driving process. Move the hydraulic peeling rig to the next pile location efficiently. Repeat the process of rig position, driving, and relocation for each pipe. Ensure all foundation support are in place as per specification. Continue the cycle until all part required for the project are driven safely to their respective position, paving the way of the next project stage with a secure foundation.
So hello, my name is Nafati Alisa and I will be presenting to you all how the fluid mechanic principles are applied in this piling system. So hydraulic piling system is rely on the hydraulic power to drive pipes into the ground. This involves the generation and control of hydraulic pressure. So Pascal's law states that the pressure exerted on confined fluid is transmitted undiminished in all directions is a fundamental of hydraulic piling system. So in this system, hydraulic cylinder exerts the pressure on the fluid which then is transmit to the force to a piston, causing it to move and drive the part into the ground. Bernoulli principle is also applied in this system to optimize the fluid flow within the system, so we can ensure that the energy losses is minimized and the maximum force is transferred into the ground. So here we have the problem example. You can read here. Okay, so the first one we need to list out all the parameters. We have the diameter, the pressure, the density, and the stroke length, and the Q. So the first one we need to calculate the force exerted. So first one we need to calculate the area given A equals to pi d square over 4. We enter all the parameters and we get 0.0707 meters square. And finally we need to substitute into the force formula. F equals to PA, and P we got 20 times 0.007, and we get 1414 kilonewton. Next we need to find the velocity. Even the Q equals to AV, and we change the position, make the V as a subject, so V equals to Q over A, and given the Q we already know, which is 0.01 meter cube per second over 0.0707, and we get the 0.1414 meter per second. So next, for question 3, we need to calculate the mass flow rate. So as we know, then mass dot equals to density times Q, and we enter the value. For density we get 850 and times with the Q 0.01, and we get the mass flow rate is 8.5 kg per second. So next we need to calculate the V stroke first, and then time strokes, and finally the total number of strokes needed to drive pi for 15 meters. So the velocity strokes, we use the formula of V equals to A times stroke length. So the area we got S equals to 15 over 1, and we get the S is 15. So the total time we use S times the T strokes, which is time strokes, I'm sorry. So S we get is 15 and times 7.07 second, and finally we get the total time, which is 106 0.5 second. So here is the analysis of our previous calculation before. So the force exerted by the hydraulic cylinder can be calculated by using the pressure area relationship, where the pressure of the hydraulic fluid and the cross-sectional area of the piston can be determined by the total force. So in this example, the system operates at a pressure of 20 megapascals and with a piston diameter of 0.3 meters, and the force exerted is found to be at 1414 kilonewton. So additionally, the flow rates of the hydraulic fluid is very crucial to determining the velocity of the piston. So the flow rate in this problem is known as 0.01 meter cube per second. Then we combine the cross-sectional area of the piston gives the piston velocity of 0.01414 meter per second. This velocity influences how very quickly the pile can be driven into the ground, thus affecting the overall efficiency of the piling operation. So, moreover, the mass flow rate of the hydraulic fluid, which depend on both flow rate and the fluid density. So this is a very critical factor for the system performance. Here, with a fluid density of 850 kilogram per meter cube, and the mass flow rate is calculated to be 8.5 kilogram per second. So this information is very essential for ensuring the hydraulic pump and the reservoir are adequately sized to maintain a consistent flow of hydraulic fluid under a bare operating condition. So finally, understanding the total time required to drive a coil to a specific drive, for example, is the 15 meters, involves the integrating this fluid mechanics principle. So by determining the volume of fluid needed for each strokes of the piston and the time required per stroke, we can calculate the total operational time for the piling system. In our case, the driving a pipe to a depth of 15 meters, considering all the soil resistance, requires approximately 106 seconds.
The conclusion is the design and operation of efficient hydraulic piling system is a true understanding of fluid mechanics principle, including pressure, flow rate, fluid velocity, and mass flow rate. This calculation demonstrates the interrelated nature of these variables and their critical importance in ensuring system performance. By accurately predicting and controlling these parameters, engineers can achieve optimal pile driving efficiency, maintain safety, and ensure reliability in construction application. Mastery of this mechanic principle is thus essential for the successful implementation of hydraulic piling system in modern engineering projects.